Hello, Math Study students. We're going to continue our discussion of calculus in our 6.5 notes. And specifically, we've been talking about derivatives, so we're going to talk about a specific application of derivatives, and that is the study of rates of change. So let's start with this. For the graph of y equals f of x, the gradient function f prime of x, or we call that the derivative, as we learned in the last lesson, that gives us the rate of change of, in this function, of y with respect to x. Respect to x. Okay, so again, this function called the gradient function is what we call a derivative in calculus. And you'll recall in our last lesson we called the derivative, it is a function, and we called it a slope generator because what it does is it calculates the slope of a line tangent to a graph for any particular x. Okay, so until now, you have only studied rates of change that are constant. Specifically, up to this point in your study of math, where you've looked at linear equations and graphs of lines, and rate of change is what you interpreted as a slope. And as you know, if if a function is a line, its slope would be constant. Well, calculus will allow you to apply mathematics to situations that are more dynamic, that are more constantly changing. Okay, so the more math you learn, the more you're going to be able to apply math to real life situations. Because as you know, in real life, you have situations where things aren't just always constant, they change a lot. Let's look at a couple of examples. Consider this function v equals f of t, where v represents the value of a car, and and that's going to be in dollars, and t represents time, and that's going to be in number of years. Okay, so as you look at the graph, you can see that as time increases, the value of the car decreases, but this is not a straight line because the rate of change is not constant. Okay, so this is where we can apply calculus to think about the rate of change at any particular point. So dv dt, which is the symbol that we use for the derivative function of our function v, represents the rate at which the value of the car is changing with respect to time. So for example, we could look at this point, okay, and at this point, if we found the slope of that tangent line, we would see that the rate of decrease would be very quick. The rate of depreciation would be that would be a very steep tangent line, and so that rate of change is a high rate of change. Well, I say high, but high in the negative directions. Whereas over here, if you look at a tangent line, that tangent line would be closer to zero. Okay, it would be closer to a horizontal line. So at that point, the rate of change of the value of the car is not as rapid. Here's another example. Consider the function s equals g of t, where s represents the position in feet of a moving object, and t represents time in seconds. So this is another case where as time increases, the position is changing more rapidly. It's not a straight line, so the rate of change is not constant. So that means that ds dt represents the rate at which the distance of the object is changing with respect to time. Okay, this change of position with respect to time is something that you'll study if you take calculus next year, or some of you will take calculus based physics, and you'll study that this rate of change, the rate that the position of an object changes with respect to time, is known as velocity. Okay, so that might be a term you're familiar with. The velocity of the object at time t. And then what if we talked about the derivative of velocity, the rate of change of velocity with respect to time? Some of you may already know this. If not, you'll study this someday in physics. That dv dt, the change here. Hold on. I'm going to scroll this up just a little bit. That dv dt, okay, would be what we would call the second derivative. Okay, the first derivative was ds dt, the change of position with respect to time. And then if we look at dv dt, which is called the second derivative, in this case, that would be acceleration of the object. Okay, acceleration is the rate at which the velocity is changing with respect to time. So now let's look at a couple of examples, and these examples will be similar to what you're going to do in your homework or on your worksheet. And the purpose of these examples is I'm kind of thinking ahead for those of you that might be taking AP Calculus next year and kind of get used to the vocabulary and the way that we describe things, describe applications of calculus. And so let's look at these examples. This first one says, the volume of water in a container, V centimeters cubed, is given by the formula V equals 300 plus 2t minus t squared, where t is time measured in seconds. So we're going to answer these questions and see how the calculus applies and what it tells us. And I just want you to write this down. This is something that, for those of you that take calculus next year, you might want to remember this little mnemonic device, woo-woo, W-U-W-U. So as we answer these questions, I always want you to be thinking this: what with units and when with units. So tell what is going on, include the units, and always tell us when that is happening with units. And you'll see what I mean, how we apply woo-woo as we look at this example. Okay, so the first part says, what does dv dt represent? Well, that's the derivative function of volume with respect to time. So that is, what that is going to give us is the rate of change. So that's the what, the rate of change. Now let's get of volume. So rate of change of volume is the what. The units would be centimeters cubed. And then that's going to be the rate of change of the water, the volume of the water with respect to time. So that's the when with respect to time. And let's give units there. That will always be measured in seconds. All right, so that's what dv dt represents, the rate of change of the volume. We're measuring it in, well, I guess we could say the volume of water in centimeters cubed with respect to time that we're measuring in segments. Okay, so now we've kind of already, the way we wrote this, we've kind of already answered this. What are the units used for dv dt? Well, those units would be centimeters cubed per second. Centimeters cubed per second. Okay, letter C says find the value of dv dt when t equals 3. Well, that's a two-step process, because the first thing we need to do is we need to define the function dv dt, okay, the derivative of t with respect to time. So in our last lesson, we learned how to take a function, take it term by term, and use the rule for finding the derivative. So let's start with this first term. This first term is a constant, and you'll recall that the derivative of a constant will always be 0, okay? The second term is 2t. This t has an invisible exponent of 1, so if we bring the 1 around and multiply it by 2, then this would be 2 times t to the 0, which is just 2. Okay, so that leaves our last term, so we'll bring the 2 around front. Remember, this last term is going to be negative, so it's going to be negative 2t to the, remember you decrease that exponent by 1, so it would be negative 2t. Okay, so that was step 1. We first of all found the derivative function. Now what we're going to do is we're going to evaluate this derivative function when t is equal to 3. So the way we write that in calculus is we say dv dt, put a vertical bar, and then put a subscript of t equals 3. So what that is communicating is that we're going to evaluate the derivative function when t equals 3. So we'll go back here to our function, and where we see a t, we're going to put a 3 in there. So that would be 2 minus 2 times 3, which is 2 minus 6, which gives us negative 4. And let's put units on that answer. That would be negative 4 centimeters cubed per second. Okay? So then the last part says, what does the answer to C tell you? Well, we evaluated a derivative function at a particular time. So remember, the derivative dv dt was telling us that the rate of change of the volume of water with respect to time. So what that tells us is that the volume of water is changing at a rate of negative 4 centimeters cubed per second. So that's the watt with units. And then the when with units would be when t equals 3 seconds. Okay? So that is one way that we could say this, okay? And what I want you to notice is that I use the word changing. I said that the volume is changing, and then I let this negative on the number tell you that it's decreasing. Okay, if it's a negative derivative, remember that means that the function is decreasing. But I want you to notice another way that we could have written it. Another way we could write it is we could say that the volume of water is decreasing. Now, since I use that word decreasing, oh, this should say at, not a, sorry, decreasing at 4 centimeters cubed per second. And then when t equals 3 seconds. Now, both of these ways are correct, but I really kind of like the first way. I want to encourage you to use this first way and use this word, use this word changing, okay? And then you don't have to worry about the sign. Whatever the sign is whatever you get when you calculated it. So if you use the word changing, then the sign of the number will tell you whether it's an increase or decrease, okay? What I don't want you to do is use the word decreasing and then put a negative on this 4. If you do, then you're saying it's decreasing at a negative rate, which is not the case here. So both of these ways are correct, but I recommend the first way for those of you that are taking calculus next year because this is just safer. Use the word changing and then let the sign of the number tell you whether it's an increase or a decrease. Okay, so let's look at one more example and see how we can use calculus to communicate what's going on with the function. So in this function we have the following, or in this example we have the following function. A company mines copper where the mass of copper X is measured in thousands of tons. The company's profit, P, measured in millions of dollars, depends on the amount of copper mined. So how much money they make depends on how much copper they mine. The profit is given by the function P of X equals 2.3x minus 0.05x squared minus 12. So I just want to point something out. Another way that we could have written this function would be P of X equals negative 0.05x squared plus 2.3x minus 12. You're a little more used to seeing a quadratic function looks like that. So just bear in mind what the graph of this function would look like. If it's a quadratic with a negative leading coefficient, we know that the graph of that function would be an upside down parabola. So as you think about what's going on here, as the amount of copper increases, the profit increases up to a point, but then there might be at some point maybe the costs get too high, labor costs or whatever gets too high, but at some point, even though they're mining more copper, they do start losing profits. So just keep in mind what the graph of this function would look like as we talk about what's going on in this function. Okay, so the first thing we're going to do is answer this question. Find P of 0 and P of 6 and interpret these results. So we go to our function named P. Everywhere you see an X, you're going to put in a 0 first, and then we're going to put in a 6. So P of 0 then would be 2.3 times 0 minus 0.05 times 0 squared minus 12, which is negative 12. And remember, that's in millions of dollars, so negative 12 millions of dollars. So what does that mean? Let's interpret that. That means that at 0, the company's starting out with a loss of $12 million. Okay, so as they have some initial costs probably of hiring people and buying equipment and leasing land and getting property rights and things like that. So when they have mined 0 tons of copper, they are actually losing money. So that's a loss of $12 million. Okay, but then we're gonna calculate P of 6. So what happens when they have mined this would be 6,000 tons of copper. So that would be 2.3 times 6 minus 0.05 times 6 squared minus 12. So you grab a calculator and you can work that out. That turns out to be 0. So it takes at 6,000 tons of copper, that's their break-even point, right? So that's the point where there is no profit and there's also no loss. Okay, that's their break-even point, and from here on they're going to start making money. So no profit or loss. Okay, so letter B says find dp dx. We're going to find that derivative function, that slope generator function, or that gradient function, and then we're going to talk about what it represents. So to find dp dx, we use our rule for finding a derivative. So we're going to take our function and take it term by term. The derivative of 2.3x is 2.3. And then the derivative of the next term, bring the 2 around front, multiply it by negative 0.05. So that's going to be negative 0.10 x to the, remember the degree will drop by 1, so x to the first, and then the derivative of the last term is 0, because the derivative of a constant is always 0. So that's our derivative function. So now let's talk about what it represents. dp dx then represents the rate of change of profit. And remember, we want to include units, so that's in millions of dollars. So I'm just going to say dollars and millions, so millions of dollars, with respect to copper mined, and remember we're mining or measuring our copper in tons. Tons, and I'm going to put thousands and thousands of tons. I hope you can read my sloppy writing. Okay, part C is going to take us a little bit of work. It says find the value of P, that's the profit function, and dp dx, that's the derivative function, when x equals 20 and x equals 25. So let's start with when x equals 20, we're going to find the value of both the profit function and the derivative function, and then we'll do the same thing when x equals 25. So let's first of all find the value of the profit function when x equals 20. So that would be p of 20. So go back to your p function. Everywhere you see an x, we're going to put in a 20. So that would be 2.3 times 20 minus 0.05 times 20 squared, and then minus 12. So grab a calculator, and that turns out to be 14. Remember, that's $14 million. This is the profit function. Okay, so now let's find the value of the derivative, dp dx. Put a vertical bar and write the subscript x equals 20. And what that is telling your reader is that you're going to evaluate the derivative function when x equals 20. So remember, here's our derivative function. So go to that derivative function, and where you see an x, you're going to replace it with 20. So that would be 2.3 minus 0.10 times 20. Okay, so that turns out to be 0.3. And remember what that unit was. That would be millions of dollars. So dollars in millions, okay, per tons, and remember that was in thousands of tons. Okay, so 0.3 millions of dollars per ton, or ton in thousands. Okay, so now let's do the same thing when x equals 25. We're going to find the value of p and the value of dp dx when x equals 25. So d of, no, not d, sorry, p, what I meant to say, p of 25 is going to be 2.3 times 25 minus 0.05 times 25 squared minus 12. So I just went back to that profit function. Everywhere I saw an x, I put in a 25. So a little bit of calculator work, and that turns out to be 14.25. Remember, that's in millions of dollars. Okay, so now let's evaluate the derivative, dp dx, at x equals 25. So that means you go to your derivative function, and where you see an x, you're going to put in 25. So that would be 2.3 minus 0.10 times 25, which grab a calculator and work that out. That turns out to be negative 0.2. And again, That's in millions of dollars, dollars in millions per tons, and thousands, thousands of tons. Okay, so the next thing we're going to do, now that we've done all this work, let's interpret what those answers mean, okay? So what I'm going to do, I'm going to stop the video because this is going to take a little bit of writing, so let me stop the video. You might want to do the same thing after you see what I've written. You may want to stop the video and write this down. Okay, so let's talk about what our answers in part C, what we got up here. What does that mean? Well, at x equals 20, remember at x equals 20, the company was making a profit of $14 million. And we can say that the rate of change was increasing because, remember, the derivative of the function at x equals 20 was greater than 0. Remember, in our last lesson, we said if you have a positive derivative, then we know that the function is increasing at that point, okay? Now, keep in mind, remember at the beginning of this problem, I told you to picture that upside down parabola in your head. So at x equals 20, the profit was, they're making a profit, and the rate at which they were making that profit was increasing. But then at x equals 25, the company was still making a profit. Remember, they were making a profit of $14.25 million. But at this point, the rate of change is decreasing. And the way we know that is because when we evaluated the derivative at x equals 25, we got a negative derivative. So the dp dx at x equals 25 was equal to 0. So keeping that upside down parabola in mind, let's look at these next two questions. The next thing we're asked to do is to find the value of x for which dp dx is equal to 0. Remember, the function for dp dx was 2.3, let's say 2.3 minus 0.10x, okay? Let's set that equal to 0 and then solve the equation so we know at what value for x the derivative function gives us a 0. So that would be negative, I'm going to subtract 2.3 from both sides, so I get negative 0.10x equals negative 2.3. Then we'll divide both sides by negative 0.10, and x turns out to be 23. So let's think about where 23 falls. And, well, first of all, let's think about what this derivative of 0 means. Remember, that's the slope of the tangent line is 0. And what kind of a line has a slope of 0? That would be a horizontal line. Well, with respect to our application, remember, we were looking at an upside down parabola, okay? So that horizontal tangent line is going to happen at the very maximum point of our parabola, and that happens at x equals 23. So when does 23 fall? 23 falls between 20 and 25. So remember, at x equals 20, the company was making a profit and the rate was still increasing. At x equals 25, the company was making a profit, but at that point, the rate of change was decreasing, so we must be over here somewhere. So the next thing we're going to do is determine P, determine the profit for this X value, and interpret what that means. So at X equals 23, that's where we have a horizontal tangent line. So let's see how much money the company was making at that time. So we're going to take 23 and put it into our profit function, and we get 2.3 times 23 minus 0.05 times 23 squared, and then minus 12. Grab a calculator. That turns out to be 14.45 million dollars. So what does that mean? Okay, that is what the profit at this point when we're at the very top of that parabola. So that would be when that derivative is equal to 0, when we have that horizontal tangent line, that's going to be the maximum point of our parabola. So that means that the 14.45 million is the maximum profit. So let's just say what it is. $14.45 million is the max profit, and let's say when that happens, and that happens when x is equal to 23. Okay, and that would be 23,000 tons of copper. So when 23,000 tons of copper have been mined, that's when the company made its max profit. Okay, so now you're going to do a couple of examples like this on your worksheet. So you might want to keep these notes handy so you can refer back to them. And if you have any questions, be sure and let me know.